So prime geometry. We want to ask, is there any geometry that factors into the primes?
It's a good question.
Right? So let's take the trivial factorization sequence. X to the 0 plus x to the 1. We've done this before, but let's do it again. Out to infinity. This is just the trivial factorization sequence, right? And when we want to do a generating function, we set this trivial factorization sequence up, all the way up, and we ask what sort of thing factors all these ways to make the thing we're interested in. Now, if we're interested in the primes, then that means we're going to put the first prime here. The 0th prime we'll call 1. Okay? 1 x to the 0 plus the first prime is
2.
2.
Yeah.
X to the 1 plus the second prime
3.
X to the 2 plus the
5.
third prime 5 x to the 3 plus and so on.
Yeah.
All right. So now we've set up our trivial factorization sequence to have coefficients that are all primes, the whole series of the primes. So we can ask a series factorization question of the primes, and we can set it all equal to 0 to ask a very important question, a question about a balance.
Okay.
So here's the question. Is there any x, any base of factorization that gives us all the primes under perfect balance? Right? That's what this equation can be interpreted as.
Well, that seems like a rather important question.
Yeah. Yeah, and beautiful, kind of simple, beautiful. Right. 1 I'm treating as the 0th prime. So okay. I'm including it in the sequence of all primes. It's like the generator of primes, right? But we're including it in the sequence. Okay. We're calling it the 0th prime. I know that's not traditional, and that's a good question too, because we want to ask something of this question, or of this from Wolfram alpha, right? We want to solve, is there any base, any x, that factors this way? Maybe there's no solutions, and then the answer is no. But maybe there's solutions. So we're going to ask Wolfram alpha to solve this equation. And the way we do that, since it doesn't recognize 1 as the 0th prime,
right,
the easiest way to write this is to move the 1 over. Minus 1, because x to the 0 is going to be 1 also, right? Minus 1 equals, yeah? Who's going to help you? What's it going to help her? Yeah. Is it a bubble? Yeah. Okay.
Uh-oh. Oh, Schroeder's kidding.
Kitten helps.
Oh, there we go.
Yeah, he's a helper. Okay. So we're going to type it in Wolfram alpha like this.
Right.
Sum of, like that. And then space n equals 1, 2, and we're going to pick some number there, comma, solve for x.
There we go. All right.
Okay,
So
bump your number up to something like maybe 20.
220. Oh, that's interesting. It seems to be converging. That's cool. Shall we continue to go up?
Yeah, we'll go up to 15. So
all right, 50. Oh, no, that's a... Oh.
So we're finding solutions, right? As he's picking a higher and higher value for n right here.
That x is trending towards 1 faster than...
So we're getting 2 real solutions that we're looking at right now. These
cool.
2 real solutions, these numbers that he's getting, are the numbers that represent the factorization base if you cut off the sequence at the number that he puts in here. Okay? And it's building more and more and more and more primes as the number goes up. What we're also noticing is that those 2 numbers, as you pick up an n that goes higher and higher and higher, the 2 real solutions converge towards a stabilized number.
It's interesting.
And the next thing to notice, if you took time to do it slowly, you find that the one solution, I'll call it x0, is slow to converge. This one converges in 100 steps, we get all 14 significant digits. Meaning the value of the number of x1 changes as you go up in n. But by the time you get to 100, x1 has already secured the first 14 significant digits, and all the changes will happen after that from then on. Okay, so it's pick the number for the first 14 significant digits by the first 100 steps. But this one definitely hasn't. So run the number up as high as you can until it won't work.
Okay.
Because it won't work at some point. Okay, and try to get what this number goes to. This number is approaching. So this number approaches the number we're going to cut off at 14 significant digits. Once it stabilizes that far, that's how far we care right now, right? So we want this one to stabilize to 14 significant digits also, and we want to know what it is. Okay? So what are you getting as you go?
Well, I just went up to 200. And
right now you're at 200, and the number is 0.979.
Right.
Okay, you go up to 300.
It's that's thinking. It's thinking.
This one converges to -1 over the Backhouse constant. It's a constant called that, which is literally defined as this constant, but it's inverse and negative. And this one is slow to converge, but if you go powers and powers and powers up in the number, it goes to -1.
Oh.
Now, how do we interpret this? So this is the solution at the limits with accuracy of 14 significant digits to the equation, the trivial factorization equation, or the generating function of the primes. Right? And the answers are going to be a number that we're calling something so far, and a familiar number, -1.
Oh, I see what you're saying. So what you're saying is when you get to basically about 100 steps out, we're to 14 significant digits. See, what I was saying is because these weren't the same.
Only for this one. That one hasn't settled down to 14 yet. Not even close. Keep going, keep going,
oh,
keep going.
Okay,
keep going.
400.
This one stays the same to 14. This one stays the same to 14. But that one keeps changing way less than 14.
Oh, all right.
Because remember, it's going to -1. So you're going to eventually see -0.99999. So it's as slow as the nines collect is the way it's going there. So what is that telling you? This is the ultimate limit, the maximum limit of factorization's base. And this is the more approximate one, the closer one. Okay, so we got two different things that happen under this factorization construction. We end up with two different base solutions, but one works at the limit and one works at down near the small numbers. If you put -1 here, 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 and all the x's with all the primes, but you let the count of primes go to a really big number, like give us trillions of primes and then cut it off. Okay, then the number works. That this actually goes to 0. Okay. Also, if you put this number instead, which is equal to this number, which is what's the values? Well, give me the digits.
The second one, okay. Yeah, -0.68677783446063.
Okay. So this number is what we want to now see more into.
Okay.
This one's less of a mystery. Okay. So we're going to use what method to look into that number now? Because first of all, what kind of answer are we looking for? We're looking for a geometric answer. We're looking for, is there any geometry that factors into the primes under perfect balance? Right? Here's the solutions. There is. It's one with this number. What does that mean? Complete blank so far. And also this one. So it's this geometry and the geometry that inverts on itself, the Mobius construction, which is a nice hint here. But we need to interpret this number in turn it into something we can make more sense out of. And we have a method for doing that now, right?
Right.
Same method for the constants of nature, which is?
The universal binomial factorization equation.
Yep. So when we apply the universal binomial factorization equation, primary action applied to some primary set of boundaries, and then it's got a binomial part, so a big part and a small part, 1 plus a terminal action on the fixed set of terminal boundaries in this prime geometry, in this minimal manifold that gives rise to all the physical characteristics of physics.
Some may call it the prime geometry.
This boundary right here is the boundary what?
It's for our break and scale, or the hinge point.
Yeah, this is the boundary of inversion in the geometry. The geometry goes from small scale actions to different larger scale and larger scale, but there's many different scales of actions being balanced. Along the way, this is the scale and collection, because this is made out of the Planck mass and Planck charge squared intersection. That boundary at that intersection is where everything that's happening inverts completely, okay, turns inside out. Okay, and it's only because that happens that we can be talking about a manifold that closes to begin with. That has to happen somewhere in the system, right? And then here's the special point in our minimal system, which happens now to be the way we're going to decode this answer. So we're going to set this number equal to this geometric construction. We know the value for this boundary. We're going to solve for this one and this one, right?
Yeah.
When we piece it apart, what do we get?
That's a good question.
You know, before I actually write down the solution, let's get a little more background to make it a little more fun. Let's do the, let's talk about, so the geometry of our minimum manifold is based on the geometry of what?
Oh, it's hyperbolic geometry, right?
Yeah, the hyperbolic.
Oh, the minimal arena, basically.
The figure eight knot.
Right, yeah.
The hyperbolic figure eight knot, or the Gaussian manifold. That's our minimal constructive piece of our hyperbolic boundaries. A way to get to our Gaussian manifold is just to take the sum from k equals 1 to infinity of sine of k times pi over 3. Now remember the pi over 3 part in there. Construction over k squared. That equals, as you sum this up, you approach the number that is the Gaussian constant.
It's very interesting.
Now, remember how our hyperbolic figure eight knot equation divides things into 1/3 and therefore 2/3 opposite pieces? Okay, well, here's the 1/3, so we need to worry about the 2/3 opposite piece.
Right.
So let's write the same thing. K equals 1 to infinity of sine of k 2/3 pi, k squared, and that now equals 2/3 the Gaussian constant. Okay. All right, what do you see so far?
So
if we're making this, then we should be making orthogonally this too. Oh, it's almost the same thing. It just happens to be scaled by 2/3 of it. Cool. So these are the two limits of the same construction, because you don't get 1/3 without getting.
You'd have to balance it out.
If you get 1/3, you also then got negative 2/3.
Right. It has to be conserved. Yeah.
Yep. Okay. Now, we'll call this the Clausian function. Okay, and the Clausian function is classically called the Clausian function, even though we're picking 2 dimensions. You could extend it easy to 3, 4, it doesn't matter.
Right.
But at 2-dimensional construction, it has this periodic repeat of the same thing. So this is the Clausian function, and it's not just at pi over 3, but at every 2 pi multiple of pi over 3, we get the same thing. And it's got plus or minus. So no matter which direction you go. If it chose plus here, the answer is plus. If you chose minus here, the answer is minus over here. The Gaussian constant.
So now is that just n as in a particular iteration, or is that red
any
n?
whole number.
Okay,
any whole number.
Gotcha. Anyway, that's because it was an n written in red.
Oh.
No, I understand what
Good
you're
call.
saying. I'm just clarifying.
Very
It
good.
just everything else is being written in red, but just for
Very good.
context sake.
Yep, I told you that ahead of time that was going to happen eventually. And the same signs again, plus or minus plus. Thanks for catching that.
Yeah.
To be some constant. Okay, so I did this twice, wrote it two different ways so that we could see that periodically in this function up to infinity, we build a structure that can continue to count forever and make this over and over. But when it does it, it's also doing this. So it's doing these two things at the same time. Riding on the minimum manifold completely and in a 2/3 way in another direction. Okay? Now, here's another thing to side note. If we put in, instead of pi over 3, if I just put pi over 3, I get what?
You get the Gaussian. Yep.
If I put in pi over 2, then what would I get?
Pi over 2, you would get 2/3, right?
Nope. This time if we get pi over 2, because it was 1/3 of 2/3. This is now pi over half, pi halves.
Oh.
Now it turns into the Catalan constant, which we're representing with a K, capital K. It's also represented with a capital C on line in both. We're going with capital K. So the Catalan constant, even if you never heard it before, now I want you to reference it as it being directly somehow fundamentally connected to our Gaussian construction.
That had come up, because it had come up as C earlier because I was relating it to something else, and that was it. Was it Catalan constant over pi, or pi over the Catalan constant, or something over 3?
The Dolman-Italian constant was that.
That's what. Okay, yeah.
Yep.
All right.
Exactly. So yeah, another direct connection to its base construction.
Right.
The hyperbolic figure 8 knot equation equals I times the dilogarithm of 1 over the imaginary golden ratio minus the dilogarithm of the imaginary golden ratio. That's it, right? It's a 2-dimensional logarithmic balance under argument of the imaginary golden ratio and the inverse, 1 over the imaginary golden ratio, okay? Right. And the difference between them. That's the volume of the hyperbolic figure 8 knot, which is equal to 2 times GGI, right?
Right.
2 times this guy. Now, if instead we put, instead of the imaginary golden ratio, we put just I. What would happen here?
That's a good question. I think we're going to see a pretty cool transformation.
Instead of 2 GGI, it turns into 2 Catalans.
It's interesting.
Okay, so this is, the Catalan constant is intrinsically part of the same balance we're talking about. It's just going at pi over 2 rotation, right? At pi over 2 instead of pi over 3. Okay, that's just cool background things to throw in. I think that's it. Now we need to return to this prime conversation and write down the solution we get.
But before we get to that, do you have any intuition on what's going on there?
In what sense?
In the transformation. Like basically how made it...
So we
not mathematically, but what might actually be going on.
What's going on is that we have a system that's dividing up intrinsically in 1/3 and 2/3 proportions.
Okay.
Trivially, it makes the minimal manifold doing this. Okay.
All right.
But also that structure at pi over 2,
right.
So it's also splitting at pi over 2. So it's doing all 3 splits. That's the intuition. They're all part of the same structure, and you can reference this split, or you can reference this split, or you can reference this split. And when you do, you get a different way of things, of construction from the same parts.
Isn't there a pi over 2 negative exponential in the hyperbolic vortex equation?
Mm-hmm.
Cool.
I'm looking at it right there. Okay. The imaginary golden ratio, which I just took out of here, it used to make the hyperbolic figure out, right? Well, let me put it back in to continue this conversation. That was a little peek. Let's turn it back into the imaginary golden ratio. So that this is once again the hyperbolic figure 8 knot. Okay.
Yeah.
Now, actually, I think I'll come to that after. Let's do the prime part. I want you to see what the intuition is now. With this background, making the minimum manifold, dividing into these balances, and the other one we just showed. How would you interpret this coming out as our factorization solution for x1? The other factorization base is supposed to be interpreted geometrically, so the factorization base of the entire prime sequence under trivial factorization. Okay. Negative 2/3 times by the Gießking constant multiplied by the Gießking constant, or I could just square it, but let's leave it at that for now. And the right-hand side is 1 plus, I'll ignore this for now because I really want to come back and have a fun story about this part, 8 lemniscates and the difference between our hyperbolic. Sorry about the crossover in equations, but hopefully you can still read this. Okay, 8 lemniscates.
Right.
J3 minus J4. Hold on. Squared, okay. And the hyperbolic figure 8 knot, according to Thurston, decomposes into what? Do you remember?
Into 2 ideal tetrahedra.
Tetrahedron, okay. Right. And those decompose into triangles.
Right.
And an equilateral triangle.
There's 4 on each tetrahedra.
If you have the length 1, 1, 1, what's the maximum corner to face side length? I'll draw it here. It's all 3 of those, but boom. So right? What's that length? If these are all 1, it's square root of 3 over 2. Okay? So if we're decomposing into these triangle connections, then that's the maximum, what we call the cusp of our decomposition. And we have how many? 6. 6 of these cusps, and we have 8 lemniscates, and 2 of our hyperbolic vortex parameters.
Right. The squared.
All right, let's talk about the first part. What would you say?
That looks like a geometry that's under action, and seeing as it's squaring itself, I think that's our good buddy the Gießking manifold turning itself inside out, or maintaining itself under some form of an action.
Yeah, it's saying that at least in terms of our primary construction, right? And the primary construction is just the Gießking manifold and negative 2/3 the Gießking manifold. Right. The positive one here and the negative one there. Right? Remember our balance? So both bases of our Clausian construction, both bases of this geometry are the primary base of the factoring of the primes. That's really beautiful, I think, right? We have the minimal constructive geometric piece under both of its constructive limits,
right,
put together to be the base of the factoring primes. And on the right-hand side now, we have it's composed of 6 of these cusps.
Okay.
Right? We decompose into 6 triangles and put them together with 8 lemniscates. What's a lemniscate?
Lemniscate is essentially the infinity sign. It's
so
under
like
Mobius twist.
Sign. Yeah, we'll go into that later. I need to erase board space for that. So this is the answer I've got here for this.
Okay.
Now, that's kind of a big hurrah, exciting moment. But I'm going to erase some of this and try to continue on extending this geometry externally.
Okay.
Okay, so if this is a 2-dimensionally constructed hyperbolic geometry, right? 2-dimensional intersection with a 2-dimensional intersection, but they're both logarithmic,
right?
The constructed intersections. On the outside, what we're doing is turning it into just the hyperbolic construction.
1 over x plus x cubed. Okay.
That's it. Now, set this equal to y. Okay, you type it into Wolfram Alpha and you ask, well, you just plot it or ask, but you can right away it'll plot its roots. So it'll solve for the roots, and you find delightfully right away that the roots of this hyperbolic construction are the imaginary golden ratio, 1 over the imaginary golden ratio, the imaginary golden ratio squared, and 1 over the imaginary golden ratio squared. Okay, 4 roots. And these are beautiful roots to pay attention to. Remember, the imaginary golden ratio divides the unit circle, right, 1, divides the unit circle into sixths. You keep going, and right? Let's see.
Right.
1, 2, 3, 4, 5. I should use different colors for that, but anyway, now you can see. So 6 pieces for the unit circle. So how many copies of itself does it need?
Okay, yeah. No, just for folks that are watching or maybe not coming across this for the first time, I was just plugging that in. The answer I was getting for that, I wasn't seeing it, and then I clicked on something else, and oh, it also has complex roots. Oh, that looks like the imaginary golden ratio.
Yep.
Okay.
Yep.
All right, that's interesting. Cool. All right,
and
continue.
it graphs them down below too.
Right.
The squares and all of them. But the thing to point out is these 4 roots are made out of only one thing 6 times. One thing 6 times, right? There's only one imaginary golden ratio in this one. It's a 1 over 1 imaginary golden ratio in this one. Now it's 2 imaginary golden ratios in this one. It's squared, right? And then 1 over 2 imaginary golden ratios in that one. So we've taken a unit circle, broken it up into its 6 pieces via the imaginary golden ratio. We've taken all 6 of those pieces so that we have our whole 1 unit circle. And we put them together under the external hyperbolic rule, under this construction, instead. So instead of just this one and another copy of this one 6 times over and over and over, it's this one and its inverse, right? See how we have 2 inverse pieces? And it's this one and its inverse as the roots of this construction. So we've put together the roots in a different way. We've flipped them and stacked these 2. Or you might notice we made this 1 power, 2 power, 2 power, or 2-dimensional, 1-dimensional.
You get stuff breaking up in different types of ways.
Yeah.
They're being decomposed. And okay.
Yes. Now, this is the base hyperbolic construction. So externally, we expect it to be hyperbolically bound because it's internally hyperbolically wrapped. So, but it's not just hyperbolically bound and goes out to infinity like an explosion with no limit of energy coming from the inside, right? It's a one that has to eventually then, under the hyperbolic projection, it has to actually invert on itself out to some maximum limit, not infinity. Okay, which means there has to be the volume part of the system has to turn itself inside out or divide about a circle. So we're going to change this equation. Remember, before we changed it, these were its roots. And these roots come from where? From the balance of the hyperbolic figure 8 knot.
That's pretty cool.
Right? This is where it comes from, literally. So the roots of that this is the external projection of that connection. But that external projection is also closed. So instead of just being these roots are going to transform now.
So those roots, they're going to take their minimal formation.
There's 2 changes here. We're dividing by 2 pi because we're wanting to be so closed its volume element.
Right.
But we're not looking now for its zeros. We're looking for its bounds. So the bounds occur exactly where there's 2 twists within the mass gap of hyperbolic geometry. So 2 orthogonal twists, pi over 2, within the mass gap. Okay, the hyperbolic geometry has this construction, right? The conic construction of all hyperbolic slices comes from this hyperbolic structure. The mass gap is what? Well, when we put this construction has three different two-dimensional surfaces we care about. Mm-hmm. The one I just drew, the cone on cone, and the...
You said three different, three or two?
Three.
Oh, you're talking about the actual decomposition.
There's the sheet, the double-sheeted hyperboloid, and the single-sheeted hyperboloid mm-hmm. that are being twisted, that are the other bounds being divided by this twisting of the mm-hmm. cone, right? We get one that's a single sheet wrapping all the way around, right. And we get these two separate sheets. And this gap that gap right there in hyperbolic geometry, the size of it determines the scale at which we're making this balance under cone-on-cone structure. Literally, that scaling really matters here. That's the mass gap of hyperbolic geometry. So we're going to put in for the mass gap the scale known as the Planck mass. All right, so that's it. We're closing our hyperbolic geometry under the size that fits to the Planck mass, right? Two orthogonal twists happening within the Planck mass boundary. Okay. You can see it pretty well. Hopefully you can see
it.
So
actually within the boundary, that is what the claim is occurring.
Okay. And then now what happens? Well, since this is no longer 0 over here, when you're solving for roots, you have to set y equal to 0.
Yeah.
Now we set y equal to this construction here. Okay. And we solve under inversion of a circle there. And these roots turn into something else.
They turn into a jus.
Yeah.
All by taking the volumetric part and mm-hmm. dividing it by a circle and setting it equal to I raised to the I, basically 2 twists around our plane there.
So you see how we would have just had this if we were going to infinity.
Okay.
Okay. If it was hyperbolic on the outside, but to infinity, so the lines just keep going straight and then never curve back around and twist themselves inside.
That's where they ultimately are converging to.
Then we stay just the external projection of this guy, but we're not. We're going to be the closed external projection of this guy. So we turn into. This is really beautiful. A transformation from this one dimension, two-dimensional number.
That's freaking awesome.
It's beautiful, right? Okay.
This is explaining a lot. See, for me, I had come on to run across this stuff. I see the just before. I remember you had kind of explained this before. You had mentioned this. We had kind of gone through it a little bit last time. Now it's sticking a lot more because we actually spent the time to run through some different constants, actually having the opportunity to actually go through the process with you. Now it's like, okay, I can see how going through the process, actually doing it, you start to gain an intuition. You realize some of these numbers, some of these constants, they just keep on coming up everywhere. It's just from our human scale, we tend to be more used to things like pi. I mean, who doesn't like pi? It's everywhere. It's something we continually use. And then when you see the subject of what basically is on the front cover of 44 right here, basically this is the generated complement of the hyperbolic figure 8 knots. So we're decomposing its volume right here. It's like, oh, this equation that you had basically showed me, it's like if we just keep running these, those come up. That's pretty cool.
All right, so I really like how directly we connect from our internal construction to our external projection, closed perfectly this way, taking our internal bits into our asymmetric external bits, right, or partition constants. Now, this is so fun.
This is cool.
It's fun figuring it out. Out of all the constants of nature, there's one that's very special.
Uh-oh. Here we go.
According to this binomial factorization construction, right? according to this, there would be a special set of boundaries for the primary boundaries. What would they be? The boundaries that match the terminal boundaries. Are there any?
There's at least one.
There's just one. The magnetic constant.
Oh.
So the magnetic constant is uniquely important if we're trying to tell a coherent story of all the constants in nature, because this would be our starting position. Why? Because if there's a constant whose primary boundaries match the terminal boundaries, then that constant represents the most symmetric fitting of the pieces that we're talking about in our balance, right? And if it's the most symmetric fitting, then it should be made up of just the partition construction here. Just those. Okay. Now, how is it made up of those? Well, there's different ways to combine those. In fact, let's remind ourselves of some of our favorite equations. Which one?
Just do the j's times all the j's. J1, J2, J3, J4.
Equals?
A circle.
A circle. Beautiful. And we're going to need actually a few of them here, so let's do them all. Let's do a couple of equations. J1 plus
2 plus 3 plus J4 equals 0.
Now I'm going to even write minus to make it very obvious. Just see the symmetry that's happening. It doesn't matter which way we go. Also 0. And then we have the squares to get our quadrants.
That gives us negative 4 pi.
Beautiful, right? The longer you look at it, the more connections you find. It's like a wiki hole of geometric algebra.
I was going to say, regardless of whether this actually helped us solve for constants of nature or not, this is just a beautiful thing, just mathematically, algebraically, and geometrically.
Okay, so one thing to remind ourselves of is that if you have a one-dimensional property, let's say we have a stick, and it's 1 meter long. Okay, we have one thing that's 1 meter long. It's one of its properties is value of 1. Now we break the stick in half, and now we have two sticks that are half a meter each.
Right.
We went up in quantity in one way and down the other value, right? So the product, though, of those two things, 1 times 1, one stick, 1 meter equals 1, right? 1 times 1 still equals 1. This we have 2 sticks times 1/2 meter equals 1. We still conserved something in the action of breaking the stick in half. We still ended up with properties that have a different distribution with the same balance.
Right.
Okay? So that's a general rule. I mean, I picked half to make it the easiest, but there's a general rule when you're dividing under balance a one-dimensional feature. If you cut something in half, you double something else. What happens if we go to a two-dimensional balance, a two-dimensional feature, and we're trying to talk about the same sort of thing?
Oh, we get all kind of wonky because we start getting area then. Or depending on we start becoming a lot more complex because we have a whole other dimension to deal with.
Yeah, now we go x squared and square rooted equals x, or x square root and then squared equals x, right? Now we pick a balance that way, where two-dimensionally we can have a squaring and square rooting that maintains the property. Okay. So over here, to remind ourselves which of these partition constants of our external domain are one-dimensional and which of them are two-dimensional. These are one-dimensional and these are two-dimensional, right? 1,
That's right.
2. 1, 2.
Because J1 and J2, they have single number components, whereas J3 and J4 have both real and imaginary components in them.
Yep, exactly. Exactly. All right, so now, given that, and we want to construct the most beautiful symmetric fitting together of these partitionings, of the boundaries on which these partitionings are balancing, right? We're going to use this construction, use the same boundaries here and there. So equals some primary action but the primary boundaries are going to be the same there. 1 plus some terminal action we're going to solve for, but same boundaries. So this is the equation for the magnetic constant. We need a primary action to solve for it, but its dimensions are exactly the same as the dimensions of our inversion in the construction of our minimal arena.
Huh.
Looked like you had more than a huh.
No, because I remember you told me that you were really excited about this because before it was kind of towards the bottom of the list. And it recently shot right
because
up to like
number 1. Because I knew the answer
one.
we had, it just didn't seem like it, well, it didn't tell me a full story or anything. And it seemed like
it could hit the numbers, but it wasn't. Okay.
In fact,
the interpretation.
It seems like obvious that this one's the most important of all the stories because it'll be the most symmetric of them. So the easiest one to tell, of least complexity, the one's only made out of our asymmetric combinatorial properties so far. So we want to now underbalance, and since these are two-dimensional, we have to achieve that. We're going to take all of our j's and say we're going to square root all of them.
Yeah.
And square all of them. Why?
Because we're balancing them.
Good. Because under our balance, we're going to say we're creating both of those, but still maintaining the closed balance.
Right.
And now what we want, whoops.
There you go, marker. There you go.
Okay.
Yep.
So what we're wanting under our most symmetric conversion is to find some sort of way that these actions are just the partition actions made from our two-dimensional balance, right? So we want to use these somehow to go into there and there. Well, if we go and check and look up one Wolfram alpha, plug in the value, the measured value for the magnetic constant, and solve for the numeric value of the primary action, you find really quick that it is equal to 4 pi.
Oh, that's pretty neat.
Which means we can pull all of the squares for its partition construction, right? We know how to tell that story. We can take all of these and say all of you are responsible for that. How? That's how.
Because when we put them together, we get a circle or a sphere.
That's positive, right? That's how. Yeah. Great.
Oh, and it's broken up into two things.
That means that what do we have left? If we're making the closed balance out of these square and the square root hyperbolic partition parameters, then in here we had to put these. Uh-oh, I didn't write down any square root equations. We don't have any hints or clues on the board. What are you supposed to do? Well, of course, we're supposed to look up what the number is.
Right.
And Wolfram alpha, find the value for this number, and then try to solve for it. But it turns out the number here is square root of j3, square root of j4, over the square root of j1, and the square root of j2. The two-dimensional square roots divided by the one-dimensional square roots. And you can rewrite that to make it look even simpler, all under one square root, right? Say j3, j4, j1, j2. Let's leave it like that. Let's leave it like that right now. Okay. And that's it.
You're serious?
That is the value of the magnetic constant. It is the structure that takes the partition solutions of our external projection of the hyperbolic figure eight not under closed revolution, inversion revolution, right? And gives us every digit we need. Beautiful, beautiful, beautiful. And now we're going to go on to the gravitational constant. The gravitational constant.
Now,
we'll draw it down here.
Now, is this on the most current poster?
No. Oh, yes. Because,
okay, because this had just moved to the top.
You can also rewrite this one as r squared
divided by square root of 2 pi. Right? Okay, yep, that's right, because it just moved to the top.
Verify that simply here, but so I have it written this way now on the current poster because I'm trying to always stick with the shortest representation. And this
you're communicating in a way.
Yeah. But when we're first showing this, I want you to see these are equivalent expressions right here. Okay?
Yeah.
So, but this is an easy thing to see in constructive manner. We're taking the quadrants, the square sum or subtraction.
Right.
Either way we're going to see it. Of our parameters, and we're taking the square roots. But we're not summing them or minusing them here. We're putting them under multiplicative arrangement, right? The two-dimensional divided by one-dimensional.
Right. That's the thing. And I appreciate you actually putting out this way, because on the board, it was basically, was it J theta squared? Or J
R squared.
It was J R squared divided by the square root of 2 pi there. But now I can actually see that it still takes me a while to get used to it. I know there's a computational equivalence there because I can do it and everything, but actually listing these things out for folks that are just kind of coming upon this now and maybe interested in helping us work on this and get involved in some way. Basically, what you're taking is, here are solutions to the hyperbolic vortex equation here, 1 over x plus x cubed divided by 2 pi, and we set that equal to what we're considering is the second half, the additional construction parameters, I raised to the I raised to negative pi divided by 2, utilizing, in this case, the Planck mass gap. We put that, we get our answer, so we have our stuff, and this is the construction of the thing that it's doing. That's freaking beautiful.
It is beautiful.
I mean, you just look at this, it's like, wait, that's the magnetic constant to all the significant digits?
And now, the gravitational constant.
Oh, we just did this on G-Day.
I think, what's the difference between, what scale is the magnetic constant dominant on?
It's typically small to intermediate scale.
And the gravitational is on the large scales of the universe, right? All right, so the dimensions, the primary action is 1 for gravity. Okay, so we're not going to even put them in, but the dimensions are LP cubed, the Planck length cubed, divided by the Planck time squared, and the Planck mass. And its terminal action is 1 plus J3, J4, J1, J2. It's literally the square of the terminal action on the magnetic constant, or the squaring, the balance point of our square roots is just back to 1. It's back at the balance point of the partition parameters.
That's gorgeous.
This is really gorgeous, right? I mean, now you're starting to see the insight of trying to get the story out of the numbers. We're starting to see how the boundaries themselves are fit together under hyperbolic partition to make the action of our universe, right? And as we understand each action in the universe, we can then use them for the things that they can do. And what kind of things can they do? They can make the things in chemistry, and they can then make the things in biology. They can make the things that we've discovered. So figuring nature out literally is figuring out how these constants, how these constant boundary intersections or actions on boundaries, the boundaries of being of what? Of the dimensions in reality itself. It's time, space, charge, mass, and temperature. So getting a relationship with those dimensions means starting to understand what reality is actually made of on a level that allows you to access it much more richly, like accessing electrons allowed us to access more of reality that we weren't even aware of before, right?
Well, we were aware that something was going on. We didn't know what was going on. It took investigation and observation and actually starting to write things down to actually figure out what is actually going on. And it's a beautiful thing because now we've identified a number of different ingredients. We have the ability to arrange them in so many different ways. And depending on how we go preparing those ingredients and the amounts of the different ones that we use in is basically what makes up everything.
And it's a simple set of ingredients. So
it's a limited set of ingredients too, so it's something we can try to start to intuit.
And here's an update from, I think, the last time I've made a video.
Okay.
The search space parameters that up until recently I've always been searching for were the powers and inverted powers of these 4 constants, plus J-R and J-theta, which are different representations of just 3 and 4. Okay? But then I would use them individually under their individual powers as the partition parameter search space. I wasn't using them in pairs. Mistake. Why? Because this partition construction exists in pairs of 2 one-dimensional partitions and 2 two-dimensional partitions. They need to be thought of in pairs.
Well, with that, essentially what you're saying is there's different combinations and different combinatorics of ways they can go together, and depending, because I remember when you were doing the search parameters, you were also double checking on some of the things that I was doing as well, because you're like, this is computationally equivalent or combinatorially equivalent, however you want to say it, of these different things. And I started to snicker just a minute ago, because the way you were talking about those different base pairs reminds me of what we heard Professor Wolfram going into on his live stream about genetic sequences and stuff like that. And apparently there's already a computational system in there to kind of see what might line up, but that's cool.
This is fantastic. So if you're following this and you're trying to do it on your own, which we heavily recommend, okay, the more time you develop intuition around this, the more you're seeing into the data points we have from reality. Right? So if you're doing that, then take this as the search parameter and that as a search parameter. Okay, this is a search parameter, that is a search parameter. You can take these to different powers, but this is just going to be that or minus. This should just be this or minus.
Wait, hold that. Are you telling us that we have the ability, utilizing technology such as Wolfram Alpha, to literally just take things that we learned in grade school, like changing the sign, like minusing things, changing it to a plus, multiplying and dividing, can help us search the actual field of reality we're claiming itself?
This is the major entrance, is as long as you understand addition, subtraction, multiplication, and division, and you know how to type some numbers into a computer. And that takes a little while. It's not but it's not a high bar. You can type these things in on your own. It's a free website.
It almost sounds like, total pitch here, this almost sounds like a new kind of science, some may say.
Yeah, in fact, a good way to think of it is it's a tool that allows anything that's conscious, so humans, the best we know of so far, right? It allows consciousness to organize and extend itself. And that's what mathematics does in general, but having a tool like this is like a mega constructor of those sorts of tools. So it allows you to ask any question as long as you can think of it mathematically. Frame a math question, go to Wolfram Alpha, start asking. And if it's framed around something like about a property in nature, the magnitude of the value of the magnetic constant in nature, if it's framed around something like that, then you're going to be using a tool to heighten your consciousness about reality.
If anyone's ever gone down a wiki hole before, going down the Wolfram hole, it's a whole different ballgame. Just because you start and again, you can always look it up on Wikipedia. Sometimes we'll do a Google search, sometimes we'll do a wiki search. Wherever you can start to aggregate your data points and you want to hone in on the most accurate data we can, because I was saying before, what I feel is the strength of this model, like many good knots themselves, it tightens up. The more information we have, the more we can actually hone in.
So he came for this conference and he didn't know whether he should tell me, but he's like, I tried one of the things that Thad put up as for the constants of nature and I got a different number. I don't know if I should mention it.
The magnetons, yeah.
Yeah, so he brought it up. And so we went and looked, and it turns out that since the last time I'd been using the numbers have been that number had been updated, right? Which is fantastic news. It means you have a number with another significant digit. In some cases, there were a couple of numbers that had, there was one that had three more significant digits of accuracy in the measurements, okay? Now, they'd also changed the base of the SI and so on, and some exact definitions, whatever, but so the point is I didn't have the updated full list of the actual measurements. So now we took the new updated ones. Some of them were the updated ones, but that made some changes and simplified the whole picture even more.
But it's beautiful. It was beautiful. That's the thing. And there were a couple of things that we started to notice that what they did for some, because in order to maintain a coherent set of units, we need to utilize the best measurements to our ability, given the technology we have at this time. And by utilizing that technology, some of them, they took a few significant digits off, but they set that as exact. So by setting that as exact point, that narrows the parameter space that we necessarily need to look, but it helps tighten up the accuracy of the different measurements in order to home in on what we are actually calculating within physics.
All the ones set to exact means that they're being used as the defining parameters. For the
They've defined it out to X number of digits that we have confidence.
Yep. So, yeah. Great. So another thing to look forward to is that, of course, then we have all the measured fundamental parameters in chemistry, which is just one level up of complexity from physics, right? So telling the chemistry story next, which of course is going to be composed of the same boundaries that physics builds from to begin with. So that's the next step to go, which we haven't even begun yet. So there's a lot of new things that will be coming. But of course, everyone can do this all on their own. If you want to take the time to start developing a relationship with asking questions about the world using the magical tool of Wolfram Alpha, the ability to ask a question that you can frame as a real good question, but literally you have no idea what the answer is, those are the ones you bring to Wolfram Alpha.
Yep. Hey.
Because it doesn't necessarily give you the answer. In fact, nothing in the world ever gives you the answer. Everything's an interpretation on some level. But what it does is it searches among all the ways that you can represent something algebraically, geometrically. You can get to the thing you just asked about with these. And you search among those, and if there happens to be one that you can make sense of, you now have something that answers your question. No, it's a process that we didn't have access to before, and it's so, you can't overrate it. You can't overrate it. It gives you the ability to go from complete blind ignorance. You have no idea what the next step is, to I have things to ask questions about that satisfy the right parameters. I can start searching and making sense of it. It's a huge ladder that, usually that moat we can't ever cross.
Right. No, and that's because I feel like a lot of people too often are discouraged, and this is something that I also took from Professor Wolf from one of his live streams. He was saying a lot of times people will come across something like, well, that doesn't necessarily seem to make sense. I'm sure somebody's looked at it. And he said that you'd often find that somebody actually hadn't looked into it. So
it's
now,
common for people to say, oh, I'm sure people looking at it. I heard all go through my career that, oh, there's people working on that. When I would come bring my questions to different professors or experts, oh, there's people working on that. And they would always list people like Edward Witten or famous names or so on. But they had this impression what they were working on was the fundamental parameters of physics. No, they're working on model generating, which is a noble, beautiful pursuit. But they're not using the numbers, the measurements to guide their insights. They're trying to be geniuses, and God bless them. I couldn't do it. I tried. I got Einstein's intuition as far as I could reach with my imagination, and I had to start all the way over. I think that's the way to go for all of
us. That's how Stephen Wolfram starts off a new kind of science.
Yeah. Which continued fraction should we start with? Which one would you say holds claim to be the most interesting of them?
I would have to go with pi. That's just visually for me that was surprising, and the sheer fact that it actually works is also amazing.
Okay, I'm going to start over here and try to write them kind of small here because it's the structure and form of them that you kind of see from a distance anyway. And start with the golden ratio. That's the traditional one we start with. 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus 1's all the way down.
Yeah.
Now, usually in a continued fraction, in the simple continued fraction, we assume all the numerators are 1s. We can modify that later.
Right? Yep.
But for now, we're sticking with that. This one's the one that also has its denominators here all as 1s.
Yeah.
So that's often considered maybe the unitary continued fraction, right?
Right. Because there's very interesting constructions, especially when you're following this continued fraction pattern. And just as a visual pattern creature, it's probably easier than to look up on rather than just seeing different things like what is the golden ratio. It's like 1.618 yada yada yada. It's like that's cool. It's a great number, but when you see it constructed like that, you're like, what's going on?
You see it constructed like this, you also notice there's something special about this number. It's the most difficult one to get to steps-wise under this construction. Why? Because it's only a step of 1 each time, and that's the minimum step. It could be 1 or 2 or 3 or 4, any whole number could be put in there, right? But this one's only 1. So that's the hardest number to get to this way. Interesting. So it's maybe instead of being the simplest representation of continued fraction, it should be the opposite one. It's the hardest to get to.
Well, it's not necessarily the hardest. It would take the longest amount of time because you're taking the minimal amount of steps.
Maybe the easiest that takes the longest. Right. Because it's only the same step over and over and over. Okay, let's look at another one. Pi. We need to update the marker.
We've been doing this for a little while. It's fantastic.
Okay, you said you really loved pi.
Yeah.
I'm going to throw in 1 for pi over 2.
Okay.
It's equal to 1 plus 1 over 1 plus 1 times 2 over 1 plus 2 times 3 over 1 plus 3 times 4 over, and so on. See the pattern?
Huh.
From here on down, the numerator is always 1 times 2, and then we take the 2 and start over. 2 times 3,
and then we do
3 times 4, 4 times 5, 5 times 6,
yada.
all the way down. But the denominators are always 1. This is one way of writing this.
Okay.
It's a beautiful way. It's a simple recursive way. Now, compare that to the lemniscate constant divided by 2. Instead of pi, we're taking the lemniscate constant. Okay?
Yeah.
And now it's going to be 1, starts the same, 1 over 2 plus 2 times 3, 4 times 5, 6 times 7, 8 times 9, all the way down. Okay? What do you see?
We changed the 1 to a 2. And then we skipped ahead from, rather than just doing it 1 times 2, we went 2 times 3. And then rather than including the last one, from 4 times 5 to 6 times 7 as well.
So the difference in numerators in this pattern to this, the denominator is easy to say. Well, since we start after the first plus, every digit down here is just a 1 here.
Yeah.
And every digit down here is just a 2. Okay, that's easy. Here we start 1 and then 1 times 2 and then 2 times 3. But we reuse the last number every time. Over here, 2 times 3, move on to 4 times 5. There's no reusing of numbers. But there are always a pair of numbers being multiplied in both cases. And we go up the scale simply in both. Catalan constant has a continued fraction equal to 0 plus 1 over 1 plus 1 to the 4th over 8 times 1 plus 1 or 3 to the 4th times 8 times 2, I'll put them in parentheses here, 8 times 2 plus 5 to the 4th over 8 times 3 plus 7 to the 4th, and so on. 8 times 4 plus.
Okay. That's interesting.
Now we can even tie that back to the one you like about pi.
Yeah.
Starts out with
it's 3.
And then 1 squared over 6
plus 3 squared over 6 plus 5 squared, 6. And then 7 squared, and so on.
Yep. All right, all of these are extremely central geometric expressions.
Right.
And they come with very relatable, similar,
we were just talking about them.
Continued fraction
Right.
representations.
Yeah. That's very interesting. What's going on?
Well, what else do we notice here? In the Catalan constant, our base is multiples of 8.
Yes.
Just goes up slowly, another multiple of 8, another multiple of 8. And the numerator is 4th powers. We're going up in odds. We're counting all the odds to the 4th powers. In pi, we're counting all the odds again to the 2nd power.
All right.
Okay, so this is the square root numerator pattern of this.
It's very interesting.
Except for one more offset. This one starts 1 here, 1 to the 4th here, and 1 squared started up here.
Squaring starts there. Okay.
1 step later, yeah. And we're also not getting this step.
Okay. So we have some built-in asymmetry too.
Yeah. Now, what does the 0 represent here? What does that mean geometrically? What you see? It's an inverse of, like here, if we want 1 over the golden ratio, then the continued fraction of that is 0 plus 1 over 1 plus 1 over 1, put it all the way down.
Okay.
So in each case, we get an inversion. So you can think of 1 over this. If you want to put the 1 in there, it doesn't matter. Okay. There's a little intriguer, or what do we call that? Teaser on continued fractions to get your mind churning.
That's the old noggin and jogging.
Let me say this: the Catalan constant is equal to. We can write it as a summation series also. So Catalan also equals the sum from k equals 0 to infinity of minus 1 to the k over 2k plus 1 squared. Okay, this is just summation representation of the Catalan constant. Remember, the Catalan constant is very directly connected to the Gaussian constant and so on.
Right.
Well, if I generalize that 2, instead of saying it's fixed at being the denominator raised to a square power, say we're going to let that power be anything you want. Let's now write the sum from k equals 0 to infinity of negative 1 to the k, just like before, and 2k plus 1 to the s. We're going to let that number be s up there. It's not specified, but it can be a two-dimensional number. Okay. S, right? This is equal to the product of the primes of 1 over 1 plus or minus prime to the negative s. Pick your s, and it sets the equation. This is prime construction.
Oh.
Now, watch one step more. The zeta function of s is equal to 1. Oh, I'm going to put the summation in there first. It's equal to the sum of k equals 0 to infinity of 1 over k to the s. Okay, and that's equal to the product of, over the primes of 1 over 1 minus prime to the negative s. That one's plus or minus. This one's just minus. And look, the zeta function, look how similar we are here. This one's a positive, so you can raise this to k if you wanted. It doesn't make any difference, right? These two are the same that way. And this one's just 2k plus 1. This one's to the power of s. This is k to the s. That's the only difference. This one's doubled and one offset. So the zeta function and the Catalan constant, this is the thing to see, I think, here. The structure of the Catalan constant is the foundation for the structure of this equation. This, if you have this balance put in place, then we could say, all right, we have that kind of balance in which s happens to be 2. That sort of thing is in play in which s is equal to 2, right? So here, let's put in over the primes, product of primes, put our s is 2. And we have a prime constructor geometrically. Are you seeing what I'm saying? Here we have a geometric way of talking about our prime construction. It's literally coming from our Catalan construction, which is which keys you into is coming from our hyperbolic figure 8 knot, our Gaussian manifold construction. The zeta function, that's what this symbol means.
Yeah.
Zeta of x minus x times zeta prime of 0. That zeta, this is the first derivative of the zeta function at 0, is equal to the zeta function at 0. So we have the zeta function has its features as you approach 0, but it also has its derivative features as you approach 0. Okay? So both of those are being talked about here, but we're making a construction asking what x can you pick for the zeta function such that when you multiply that x by the derivative at 0, you can take the difference and get just the derivative at 0 left. So you can, it's a self-symmetric balance you're looking for, okay? So, sorry, just the zeta at 0 left. So we're closing our functional parts and asking what x, what scale, if any, maybe there's no solutions. But if you go look and check, there's a solution for x equals our terminal boundaries, our Planck length times Planck mass over Planck charge squared, this scale.
which coincidentally comes out to be 10 to the negative 7th power.
Yep. Now, and you can probably already guess, there's the same x that solves this equation in the gamma function. What are you seeing?
That's very interesting. Well, it's looking like a balance point of some sorts. It looks like at that particular scale, something very interesting is happening.
Yeah. The gamma function is coding how the boundaries hyperbolically divide, and the zeta function is just a double cover of the gamma function. It's a double copy of the gamma function put together. That's what it is, right? So, yeah, and one of them's centered at 0, the boundary. The other one's centered at 1, the projection, right? So we hyperbolically divide up our projection under a certain balance, under a certain scale that balances this balance perfectly. But at the same time, on the other end of things, not at the projective end, but at the boundary of things, we divide up under that.
Is this way? You had mentioned something the first time we had spoke, when you had come on my channel before, about the ability to, some folks say they should twist the metric, but in what way could you twist the metric in a way that things would stay symmetric? Because I remember from the other day, wasn't it something about zeta of 1? We looked that up. Didn't we get infinity or something?
Yeah. It's not defined.
Right. Because in infinity, but if we could set up bounds on that affinity, you'd allow. Okay.
Yeah, but it is at 0, and vice versa, right? So these are where they have their best definitions. But it's great to see the symmetry between the two, right? They're basically the same thing, minus this one x difference, right? They're the exact same construction, except for this one's on the argument of 0, and this one's on the argument of 1. Oh. Okay, also, what do I mean by 1? Literally the 1, the unit. Remember the one that the imaginary golden ratio to the 6th power equals. That one, that's the one that everything's being divided. The one is the projection that's being hyperbolically divided. Yeah.
That's fantastic.
It's just the arena. Okay, that might be close to the end of that part. Oh, I wanted to then go into, let's do a quick review again on basic two-dimensional geometric shapes.
Okay.
Yeah, and then we want to go into look at the hyperbolic internal construction, that conic construction that has the double-sheeted hyperboloid and the single-sheeted hyperboloid.
Right, the things that come together
by the intersection, right? We're going to look at the hyperbolic boundaries themselves and ask, what's the inside doing?
What's going on?
Okay, we're going to ask, if we know that these are hyperboloids, if we know exactly what these boundaries are, then what's the inversion of the boundaries? What would the inside be experiencing? Literally, how do you define the inversions? So, great.
Groovy.
And there's going to be a surprising connection to a very, very popular root of fractals coming up here, known as the Mandelbrot set.
It sounds like we're about to go fractal, Thad.
We're about to understand how hyperbolic geometry is fractally maintained. Now, we already have on the equation for the charge boundary, literally from the very beginning, there are 5 boundaries, or Planck constant boundaries.
Yeah.
The way that the charge boundary is hyperbolically dividing defines what you might call the most trivial fractal, the Weierstrass constant, the Weierstrass fractal. Oh. Right? So, all right, we'll start with two-dimensional geometric shapes.
Okay.
Why? Because our partitioning of our balance is going to be comprised of 2 dimensions intersecting 2 dimensions in many, many places. So we want to be very familiar with all the two-dimensional basic geometric shapes. First place to start is, you might think of taking the unit circle. Right?
Okay.
And we'll think of this as the limit of a whole collection of possible shapes. The regular polyhedra. I can put in a square, this would be the 4. But we also have, before that, so inside the unit circle you can fit shapes that divide the circle into whole numbers of pieces, beginning at 3. Okay? I guess you could cut the circle in half, but we're talking about geometric shapes that have volume, or sorry, that have area. It needs a non-zero area. So the first one's a triangle and it has 3 sides, so it divides the circle into 3 things. And by regular we also mean that the shapes have equivalent sides. Okay, so we're going to introduce just the fastest way to talk about all shapes. It's a circle being divided into 3, triangle, 4, the square, 5, and we keep going up until we get closer and closer and closer, approximating the circle. So the circle is like the infinite limit of polygons, right? Okay, unit circle means we're using the scale here. This is distance 1, radius of 1. Okay. Next, in hyperbolic space, or in hyperbolic geometry, we have the base construction of hyperbolic geometry is this conic balance, this cone on cone construction between everything. What do I mean by that? I mean, when you take a two-dimensional slice, any kind of two-dimensional slice you take of this construction, intersects it with a boundary that defines a hyperbolic shape in geometry.
Right. A
well-known one. In fact, well, there's infinite numbers as we go change our angles of our slice here, but if you slice perpendicular to the pole, imagine the middle is going up here, or slice right in like this, then you're going to get a circle.
Yep.
Right? Now note, if you get circles, you must be either in the top cone or the bottom cone. You're not in both. You're the top or the bottom if you got a circle. Good thing to note. If you change your angle of the circle like that, but you're still just slicing through the top, now it's more elliptic. And a good way to see ellipses is they have 2 foci. Right? Let's make this a little bigger. If you have an ellipse touching here and here, let's say it's going to focus down, it's going to have a focus here and here, let's say. Okay? What does that mean? What are you supposed to visualize geometrically? It means underneath this plane that we sliced, there's a sphere that you can fit into this cone, and the sphere touches that point. So there's a certain size sphere that can fit in the cone and just touch that point. And above, there's a different size sphere that just touches that point that snugs into there too. And those are the center, or the foci of our ellipse. Okay, so literally our ellipse in conic hyperbolic construction, ellipse is separating 2 spheres of different size. And the more elliptical you go, the more the difference in size will be. Okay, that's really beautiful to see. Now, what other shapes are in our construction?
Well, we've also got the lemniscate.
Oh, in this construction, continue slicing it two-dimensionally.
Parabola.
Yeah, we can slice it now this way.
Or we could do a
up in that one, or yeah, it depends now if we go into slicing the top and the bottom at the same time, or we stick into just slicing one or the other, right? Now you can also, well, let's do a parabola. A parabola and a circle have 2 very unique characteristics. They're inversions of each other, right? This one has a radius, we'll call it 1. This one has a foci. The foci now, if you zoom out from the parabola, and you're considering a larger and larger portion of the parabola, your focus changes, okay?
Yep.
And there's going to be a distance. Well, we take our focus point and draw a straight line, like a level line. It's called the lattice rectum. And we can then take the distance of the line or the parabola between the ends of the lattice rectum. This curve right here has a certain length. Like if you lay a string out on it and then straighten it out and measure the length, okay?
Right.
That length divided by this length equals the universal parabolic constant. Just like this length divided by this length,
pi.
The whole diameter equals pi. Okay, so this you can think of as a circle turned inside out. But the thing you really need to remember is the circle is unique in that you could zoom out or you could make a bigger circle, or a much bigger circle, or a very much bigger circle, and it doesn't change that constant being represented in the circle. Same thing with the universal parabolic constant. If you choose to zoom out and look at this thing thousands of miles up, well, your focus point moved up, but the ratio of the curve that you have access to and this distance stays the same, just like in circles. Exactly the same. So, two universal constants built into this hyperbolic construction. You can slice it all the way down to perpendicular to the pole here and get this guy. You can be this way, perpendicular to one of these, parallel to one of these boundaries, slices a parabola. And then if you slice both of these, you come in like this, and slice down like that, you're going to get the hyperbola. Okay, so we have circles, ellipses, parabolas, which are inversions of circles, and hyperbolas. And these are all just defined by the limits of this construction, of that bound between everything, and how you slice it, that construction. Okay, fantastic. Next, where's my notes? Over here. Lemniscate and cardioid. All right, so let's look up lemniscate.
It's basically, when you're looking at the picture, it's essentially you have an hourglass with some spacing in between it, and consider if you had something straight like a meter stick, and how could you transition from touching all the points on one to that balance point where you're literally having a handoff to the other sheet?
Yes, yes. And the red dot is in the middle of the line, and it moves around as we just wrap this line, right? It's being touched and rolled, and when it hits the other side, then we roll it this way.
It's being
and we just keep rolling back and forth.
Being completely traced out by the lemniscate, or what we colloquially refer to as an infinity side or a sideways 8.
Yeah. So they call this the pedal curve of the rectangular hyperbola, or you can think of this as the inverse transform of the hyperbola.
Or figure 8.
Yeah, or figure 8. But the thing I really want to have us notice right now is that it is an inversion of the hyperbola.
Right.
It's, in fact, in this picture you see it really well. It's what you would expect to find inside the hyperbola. Okay. Now, what about cardioid? Does it relate to anything in this kind of geometry?
Oh, I love it. Yep. When you have, an equidistant circle tracing out on the outer boundary of another circle, after it goes a full 360 degrees around the inner circle, it will touch again.
So anything that fibers into a bunch of strands, the strands will move around each other like circles, right? But that tendency to wrap around each other would form this shape, no matter what. Any two circles of same size rolling around each other trace out that shape if we pick one.
Utilizing one single point. Yep. Okay.
Okay, but what do we want to think of this curve as? That path that follows, what kind of path is it? Well, it's the inverse curve of the parabola.
Oh.
It's literally the inverse curve of the parabola with the focus at the center of inversion. Okay, so now we have inverses of hyperbolas and inverses of parabolas, and this is the shape that makes hyperbolas and parabolas. So what's the inside going to look like that's holding this shape together? It's going to be made up of
hyperbolas and cardioids.
Or lemniscates and cardioids.
Lemniscates and cardioids.
Inversions of those two kinds of shapes.
Okay. That was the old picture. Okay, got it.
Now, I told you there was going to be a really cool connection to the Mandelbrot set. What's the predominant shape of the Mandelbrot set?
It's cardioid.
The cardioid.
Yeah.
What's some of the features? So we'll pull up a picture of the Mandelbrot set. Let's look at some of the outstanding features really quick that you might want explanation for.
The Mandelbrot set is a set of complex numbers C for which the function f sub c of z equals z squared plus c does not diverge to infinity when iterated from z to 0. When you start to zoom in to this, apparently it really just depends on your resolution. It keeps going.
It keeps going in, but the limits out are +2 and -2. The picture that the spike doesn't keep going forever this way. The more you zoom in, it limits it, -2 and +2 the whole picture. That's one thing to note. So 2 and -2, that's just double 1 and -1. We really care about our unit circles. Kind of interesting. This is a bifurcation structure, we're thinking. Okay, so 2 would be an important number, but there's this spike way out here. Let's click on the picture real quick.
Okay.
Other than the main feature being that we have a cardioid, which we form by rolling one ball around another, we also have that sized ball sitting outside of it next to it. So one ball rolls around another, and then we have the size of the ball that does the rolling right there.
Yeah.
And then this thing does itself repeating shape, but it ends up making this next big, this like, let's call it a vertex.
Okay.
Okay, let's think of that in the general shape as a vertex
Yeah.
of the picture. Think of this now. We have a circle I'll put in between these bounds. And the inversion of the circle, meaning you're using circle inversion to cross from inside and outside the circle like it's a mirror. That blue part maps to this blue part. This red part maps to that. This green part maps to that green part, right? So that's what we mean by inversion. And if you let the circle go all the way to touch, then these will touch too.
Yeah.
So that's what we really want, is the touching ones. But now, I'm going to assert this, that in between these boundaries we have a lemniscate maintained, the inversion curve, and we have two of these cardioids. Why? Well, we put one cardioid in here.
Right.
And if we put in a second cardioid there.
Yeah.
And then we say, wait a second, my favorite cardioid is
the Mandelbrot set.
The Mandelbrot set. Let's scale it to match perfectly right there now. To fit inside of our hyperbolic construction. What does it look like? That vertex becomes the focus of this side. So you throw in this one, and both of those focuses now have internal constructive balance. You see what I mean? Symmetry happening here. So there's a lot more to say, of course. This is leading and just a start of a conversation. But the point is, we're noticing we can think of the internal construction of hyperbolic geometry itself as being maintained under these two kinds of balances, right? And therefore, since we thought it was the trivial fractal to begin with on the charge boundary, we're going to be looking at this constructed, literally the prime constructive anyway. We're already thinking that this is the prime geometry. So all the prime numbers are contained in this sequence, all in fantastic ways.
Well, this is the beautiful thing. And I remember you had quickly showed me that the other day. I created a connection, and now I didn't actually realize that was exactly what it meant. I'm like, okay, we're kind of lining up. But it really does look like if this fascinating fractal that has all these properties and it's freaking beautiful. I just stared at it for the past minute of it, zooming in further down on the page. But you literally have this joined with this. You have your central balance point. And at that point, I don't know if we could map out the actual transitions from that to that. If it is perfectly balanced, maybe it could
Think about inside our hyperbolic figure eight knot. We're saying that the first balance that's made is a two-dimensional circle, and outside that there's going to be then 6 other things expressing that circle. Right? Making our next scaled balance. When you see this shape, you know it takes 2 circles of the same size to make. Right? Okay. And there's a third one right there. So this picture's got like 3 circles making it. Right? 3 same size circles making it. 1, 2, 3. The other one would have 3, 4, 5, 6 in the balance.
Because of the size difference.
Yeah, the 3 circles constructing that one, the 3 circles constructing the other one, right? And over this middle is where our
for them coming to
yeah. That's what I'm saying. I'm seeing that this shape is composed of 3 identical sized circles.
Well,
our shape decomposes into 6 identical sized circles outside here. So 2 of the shapes is the decomposition structure of that fractal geometry. We're assuming a hyperbolic geometry. So this might be kind of the end of where I was going to go. But yeah, it is. I just wanted to bring us to this beautiful connection between the Mandelbrot set, which a lot of people have spent some time developing intuition over, or at least appreciating.
It's fascinating. I've stared at that thing for a while.
And the story of hyperbolic geometry. That's the connection we're really trying to point out here, that we have a natural connection between the hyperbolic space-time, four-dimensional hyperbolic space-time construction that Einstein revealed, right? A natural story between that and the internal shapes being cardioids and lemniscates. Oh, lemniscate, one more thing I can say about lemniscates. Cool. This maybe be an introduction. So the lemniscate that we really care about here is going to be the one that goes out to 1. I made a mistake about this earlier, so it's good to do it correctly. It goes out to 1, and it's like a circle, but it has to go through its own center, or like an ellipse, but it has to go through its own center instead of across. So this is the lemniscate of Bernoulli, the unitary lemniscate. Okay. Its length is what? If this length is 1, what's the length of that curve? There's got to be an exact number, and it might be useful. Like, is it pi? Is it 2 pi? Is it anything related to pi? What is that number? Well, it's represented as s. The whole length of this lemniscate is s. So arc length of the lemniscate. Okay, s isn't the lemniscate constant. It's the whole arc length of the lemniscate. The lemniscate constant equals s over 2, which means it's the arc length of just one petal.
Huh.
That's kind of a unique number in here anyway. And also, you'd think that one would too, because it's divided up exactly in these balances. So, turns out L1 equals L over 2, which is S over 4. So yeah, we have 3 of the lemniscate constants now are just easily seen here. S is all of that. L is just this or just this. L over 2, or sorry, L1 is L over 2, and that's just 1/4 of the whole path, or 1/2 of one petal.
Right.
Great. So that's the lemniscate constant there. I didn't give you the digits. This is how we represent it, like we represent pi with a letter. All right. One interesting thing that might connect to everybody who took any training with cosines and sines.
I remember I got taught it, and I just didn't see any. I got very bored and doodled in my notebook.
Here, if we start at 1 and we do sine or cosine, it doesn't matter. We go up to 1, goes down to -1, back to there, right? Sine wave, traditional unitary, supposed to be touching there, -1. This is the unitary sine or cosine wave length, and it just shifts if it's sine or cosine, right? So the value here is 2 pi. When this is 1, this is 2 pi. So this single, most familiar wave decomposes into units of 1 and 2 pi. We have scales we care about, 1 and 2 pi. Great. What else is in this unitary sine wave, unitary cosine wave?
Oh.
An arc length.
Yeah.
This length from here, put the rope and drop the rope here and figure out how long is this path. This straight path is 2 pi. This straight path is 1 and this one's -1, so total is 2.
Right.
Okay, but this wiggled path has a different length. It has a specific length to the unitary cosine sine wave that we're all used to using. What is it? Well, that length right there is equal to, we'll call it the length of this sine wave, or length of the cosine wave. They're equal. That arc length is going to be 4 pi divided by s plus s. S is the arc length of the lemniscate. The circle divides up into the cosine and sine. The sine and cosine divide the sphere using lemniscates.
That's fascinating. Why?
Because they're back and forth, back and forth.
Because it's twisting and it's okay, it just happens to come out to be that ratio.
Out. Yep, back and forth, inside out. Okay, so there's a connection. If you've never had a direct mathematical connection, how to see why would I care about this constant or this constant or that constant? Well, if you got to the point where you've seen how we decompose circles into sines and cosines, well, sines and cosines both have this magical number fixed into their unitary wavelength expression. There it is. Takes us right to arc length of the lemniscate.
I think the first time I ever heard that was during some of the Wolfram Physics Project's live streams. I remember Jonathan Garrod, shout out to Jonathan, he'd been mentioning that, and I'm like, I didn't even know what that was. I was already looking up so many different things, and just even the past couple of days, it's just, there's so much out there. It's not one person can know everything, so it's like the ability to write it down and have access to that information. I think that's a total game changer.
Yeah.
Cool.
This is beautiful, isn't it? Basic geometries telling us stories now.
I feel also some of the history and kind of how we got there too helps put a specific context to figure out, it's like, how did we actually get to this? Because actually going through the process, if we know what people did before, we can refine the process.
That's what we're trying to do, is keep making more and more sense of this, get more and more clarity about the primes, about all the questions you could ask about the primes, or about hyperbolic geometry, or about physics, or chemistry, or biology. Yeah, it's the process, though.
Well, and that's the thing. I look at some of these things, and there are a lot of really talented people out there, and I've had the benefit of interacting with a number of them. And if there's anybody out there that has a particular set of skills, and they really feel like this is something they would like to investigate for themselves, let us know. I think that'd be pretty cool.
Yep. All right. Cool.
Sweet.
Till the next conference.
Absolutely.
Or the next video.